Here you go. Share. Okay, I hope everyone is able to see my screen here. Okay, so the first thing I'll do, I'm gonna send you chat. Okay, can everybody please, I just put a link here on the chat. Can everybody please copy paste that link on your web browser? The web browser is preferably Google Chrome. You can use other browsers, but Google Chrome or Firefox would be preferred. Would make it easier, and all the features can be running. So please have a look at this link, and this is a Python notebook. So what's a Python notebook? Right now, the fashion or like the trend in doing Python or machine learning tutorials using Python is, instead of doing it all on PowerPoint, all the static text and all that stuff, slide by slide and so on, people have started doing something different. They're using what's called a Jupyter notebook, because what's cool about Jupyter notebooks, which is an example, is the one that you're seeing right now on my screen, is that you can actually run code in it. I mean, while I'm discussing, so I'm going to be taking you through all these, and in the middle, I'm going to go here, for example. Guys, this is actually some Python code. It's a print statement. So I'm going to go and click play. And this is actually Python running. Thanks to Google, it's actually running on Google's servers. So I just want to make sure first, did everybody get the link? Copy paste it. Once you do that, it's going to take you to my Colab notebook, which is a public notebook. However, of course, during the session, I mean, it will be great if you can just have a look at the notebook through the shared Zoom screen. You don't have to go around and download or open the notebook on your computer and do things on it. You don't have to do that now. If you wish, you can, of course. It'll actually be much better if you can run the code snippets here while we're going through the notebook. But for now, let's just focus on this notebook. So this is going to be our lesson today. So this lesson is going to cover, I hopefully through 40 minutes, is going to cover a little bit of Python, how we can write Python on the browser and run Python on the browser using Google Colab, bit of Python, how we can get materials data. So data for materials is now, there's a lot of data for materials online. And one of the very nice materials databases is the materials project database. So we're gonna have a look at this one and how we can access it. And the main objective of this session is to learn how to do with Python, access the materials project database, use a Python library to access the materials project database using Python, and open the CIF files or the crystal or the material crystal files that you can download from materials project. I hope this makes a clear case for everyone what we're going to be doing today. Learn a bit of just a bird's eye view of machine learning, a bit of Python on the Google Colab, and then materials project database, and then PyMatGen Python library, and then a little bit of how we can open a structure file, and then querying PyMatGen or querying the materials project database via PyMatGen. I really hope this will be good enough, to give you like an overview of the, of the day-to-day details of working on machine learning with Python for materials. Next session, we are going to be using what we've learned today in order to predict the band gap of materials. So we will be actually doing it together. We are going to retrieve materials, calculate the properties, and then predict the band gap for these materials. Details and the content will be coming soon. I mean, it's a funny coincidence that a few minutes before this session, I destroyed my blog. I had a blog post, a nice one actually, that had all the information, and through which I was going to share all the video for the recording and the material and everything. But boom! So That's why I joined in like a 1 minute or 2 minutes late. Apologies for this. I'll try to fix it after the session, but for now, let's just start. So machine learning for material science. So it would be great if you have a little bit of coding experience, C, Python, any language, Pascal, C#, JavaScript, anything, the conception of procedural or writing procedures in a programming language, interacting with the computer in this way, having this sort of experience would be great. If it's not the case, it's fine. Let's just keep going, and I hope you can catch some programming as we go. The cool thing about Python, not just that everybody is using it now for machine learning, it's also because it's a very easy language to use. And I'm going to type this here again, just to emphasize. Python is very easy to learn and use. Python. That's one of the key things. It's very easy for you to learn Python. I'm going to go through a lot of Python within a few minutes here on this in this Zoom session. And I'm going to point you later to YouTube, where there's a huge amount of Python tutorials. You can really learn a lot of Python just on your own at home, even without having Python installed. It will be much better, of course, to have Python installed on your computer, but you can still learn the basics just on the Colab. What I'm opening here, by the way, is the Google Colab. How I can access Google Colab? I just go new. Just Google Colab, and here's a link. Let me actually look it up. Colab, happened. Google Colab. Link is here. So colab.research.google.com. You go here, and then I've got a couple of notebooks, Python notebooks here. I don't need any of those. That's like an introduction to what the Colab is and how it works. The cool thing about the Google Colab is, let me actually file, new notebook. Colab, or the Google Colab, lets you open up or create Python notebooks. They're called Jupyter notebooks. In these notebooks, you can actually run Python. Seems that I was supposed to admit people. I'm really sorry for people who have just joined us. Apologies for keeping you in the waiting room. I really forgot to press the button. Sorry about that. Okay, so the Google Colab, you just open it, and I can write Python here. Let's say a equals 4, b equals 6, print. Let's just go c equals a plus b. That's Python coding, by the way. It looks pretty much like MATLAB, doesn't it? Or even just a Casio calculator for now. It gets more complicated, but it can be as easy, as simple as that. And then play. You know what I'm doing here? I'm actually running Python. So I wrote Python and I'm running Python. It is running on the cloud. So this is a Google Cloud that is shared for research purposes by Google. Thanks to these guys, you can actually use the compiler, the Python compiler, on the cloud to run your own Python code. And that's really cool. Really makes it much, much easier to learn Python this way. Okay, a bird's eye view on machine learning for materials. So what do we do? How do we use machine learning in material science? What is machine learning? To start with, machine learning is, you have a set of materials, and you want to predict their properties. So there are two key things that we use machine learning for in material science: classification and predicting a quantity or regression. So you either predict that a material is a bandgap material or a metal, like metallic or semiconducting. These are examples. So let's say, for example, one of the machine learning problems is whether classifying a material if it's metallic or semiconducting. Likewise, if it's a high temperature superconductor, low temperature superconductor, if it has a high photovoltaic figures of merit, or low figures of merit, or whatever. If the material, you can predict the specific heat capacity of a material. I'm pointing you here to my own paper. Now, so this paper, I published it with a group of great minds here in Australia, and in the collaboration with Alexander Isayev in the United States, predicting the specific heat capacity, which is a very useful quantity using machine learning. and with Python. The code is also available on this blog. And apologies that this blog I broke it 5 minutes before the session. A very silly mistake. So I'm gonna fix it, and I'm gonna let you know via an Eventbrite email. The homo-lumo gap of a molecule, again, that's a very important problem to use machine learning for. So you can use a machine learning to predict the homo-lumo gap, atomization energy for a molecule, and so on. And that's a paper, an example paper for that sort of stuff. And again, the broken blog, that's quite bad that I broke this blog. Anyway, I'll share the unbroken blog once this session is done. Okay. So how does machine learning work? Let's start by let's just take a bird's eye view of how it works. First of all, we're dealing with materials, right? And a material can be defined by the atomic structure or by some of its features. So you want to define the materials. Let's say you have thousands or millions of materials, whatever. Then for each of those materials, you want to represent it. That's the first thing, that's the most important thing. You want to represent it by a set of descriptors. And these descriptors that's pretty much like an array of numbers. Each one of those numbers, represents some information about the material. So again, first thing is we need to create descriptors. So a descriptor for a material, a set of numbers. Next, we want to create an Excel sheet of descriptors for all the materials that you have. And that's what we actually call the material dataset. So we want to create a dataset. That's when you hear people talking about datasets. What a dataset is, it's all the materials, along the, along the y-axis here, and their descriptors. And then for each of these materials, there is a quantity that we want to predict. Let's say these materials 1, material 2, material 3, carbon, graphite, let's say MOS2, iron, some alloy of nickel, some superconductor, blah, 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 blah. These are all materials, and each of those lines is a set of numbers that describe each of these materials. These numbers, again, are called the descriptors. Now, each material has a property which exists in these, in these cells. One property for the materials could be the band gap. So we can put, like, for material 1, here's the band gap. Material 2, here's the band gap. Machine learning takes this stuff, these numbers or these sheets, and enables you to use those descriptors to predict the property for a new material, for a material that the machine did not see before. Let's say that you have 1,000 materials and you already have descriptors for those materials, and you want to predict the band gap for these 1,000 materials. Machine learning lets you predict the band gap for materials not inside the initial data set, not within the 1,000 materials. That's the real power of machine learning. You're creating a model using biologically inspired, that's why there's a human brain here, biologically inspired algorithms to predict or to build models to be able to make predictions. Okay, so step 1, descriptors, step 2, dataset, and then step 3, or C, machine learning. Okay, so before we get deeper into the machine learning here, we want to just go quickly through Python. Just a little bit of Python programming, and then we're going to discuss a database for materials. Database of materials, that's important for machine learning because we want to find a place where there's a lot of data, right? Okay, so let's start. First of all, Google Colab, that's what we're using here. And as an example of Python code, a print statement, that's the simplest I can go with Python. Just one statement that prints out something. Hello material science, that's just a print statement that prints this text here. Notice that the text is enclosed by double quotes. In Python, you can enclose text with double quotes or single quotes. In Colab, you can run this code just by typing, by going click on the play button, and now this has been printed. We can go, hello material science, happy you're here, whatever. just in case you don't believe me, I can just play, and there you go, boom. Okay, so the print statement prints out stuff. Well, I mean, yeah, there's a lot more in Python. The key things, I mean, important things in Python, I just go really, really bird's eye view here. You've got all this shared, and it's yours. You can use it. You can play with the stuff and learn after the session. But for now, just a quick intro. So basic Python, variables, operations, if statement, and the for loop. These are the things I'm going to try very quickly to cover. Print statement, I just covered here. That's a print statement. Do you like coffee? Yeah, like coffee. Print statement can have strings separated by commas. So let's say print like coffee, comma, yes, with milk, please. So it's gonna print out like coffee, space here, and then yes, with milk, please. A string is a type of data, or it's a data type in Python. And a string is either surrounded with like double quotes or single quotes. So double quote A, double quote, that's a string. This also is valid, single quote, a single quote. So in Python, you can surround a string with a double quote or a single quote. Now, in programming, I've probably heard of variables. In Python, we can use, we can just create variables as simple as this. S equals I love coffee. That's a string variable. I filled it up with I love coffee, and that's a string value surrounded with double quotes. So I can just go and then print S. So S now is a variable that has a value I love coffee. Plus, minus, multiply, divide, these are arithmetic operations that you can do with numbers. This is the modulus operation, and this is the, what's the name for it? The divide operation. I forgot its name. What the modulus operation does, it gives you the remainder. What divide gives you, it gives you the result of a division without the decimal part. So for example, 9 divided by 2 is 9 divided by 4, for example. What's 9 divided by 4, man? Okay. 5 divided by 2, 5 divided by 2 is 2.5. 5//2 is going to give you 2. It's going to remove the 0.5. 5 divided by 2 is 2.5, that's the result, whereas 5 percent sign 2, which is the modulus, is going to give you the remainder, which is 1. So 5 remainder 2 is 1. Similar thing, 9 remainder 4 is 1, because 9 divided by 4, I think it was, I forgot. Anyway, 9 divided by 4 is 2.25. Yeah, so 9 divided by 4 is 2. 9 ampersand, or sorry, not ampersand, 9% 4 is going to be 1, which is the remainder of the division. Comparison operations, these are like logical operations. They ask questions. Like if A is equal to B, A equal B means is A matching B, or is A exactly equal to B? Not equal means, yeah, not equal. So A equals 3, B equals 5. C is equal to A equal B. So C is going to be a Boolean. It's going to be a logical value. Now, I mean, from here, what do you think? Is C true or false? C is false, because A is actually not equal to B. Saying that A equal B is actually wrong, so C becomes false. Lists. So one of the key things in Python is how it organizes things into lists. Lists are like arrays in other programming languages, and the way to create a list is quite easy. A equals, you just open a square bracket in Python, and then you put the stuff separated by a comma. 4, 6, 7, that's a list of numbers. That's actually 5 numbers here. How can I access the things in this list? I just need to use square as well. Now in Python and in many other programming languages, the index for the elements in the list start from 0. So the A of 0 is 4, A of 1 is 6, and that's A of 0 here, okay, is 4, A of 1 is 6, and so on. Here A equals I, 1, 2, order. That's a string of, that's an array of strings, or a list of strings. A of 0 is letter I. That's the first element in this list. So 0 is the first element. Always remember, that's a very important bit to remember about Python. Here in this list, A of 5 equals, yeah, so the thing is, in a list, let's say I start with this list here, I can change the values, right, of the elements in the list. So I start with this list, and then I specify that 5, element number 5, which is the 6th element, becomes yes, you can. So if I go and play, I want to, yes, you can. That's the 6th element. So 1, 2, 3, 4, 5, 6. Indices 0, 1, 2, 3, 4, 5. That's the 5th one. Now, question. I know that time is running. They only give us 40 minutes. Is it easy sounding for everyone? Am I missing anyone? Is it all good? You can type text. Okay, cool. Okay, tuples. I'm gonna leave you with the tuples. Tuples are lists that are immutable, so you cannot. Thanks, guys. So tuples are lists that cannot be changed. So it's the same concept as list. You just you cannot change the elements of a list. A equals 3, 4, 5. A of 0 equals 2. When I change the first element of a tuple, I get what? You guys see this? I get an error. There's an error here, and the error is due to the fact that tuples are immutable. I cannot change tuples. Okay. Dictionaries, that's one of the very important data types in Python. A dictionary can arrange or can create a list of things, not really a list, but it can create a collection of things that are labeled. So I can create a collection of fruits. Okay, the label or the key is the fruit name. The value of each element, so that's the element. Apple colon 3.5, that's one element in the dictionary A. That element has a key and a value. The key is before the colon, the value is after the colon. Apple, that's the name, that's the key. That's 3.5, let's say it's the price, 3.5, that's the value. So a dictionary is a collection of key value pairs. That's why they call them key value pairs. If I want to print out the value of that key value or that element, I just go A, open square, bracket, and then Apple. Let's see how this is running. So when I print a Apple, I get, so you see, 3.5. B, now I can actually put, for values, I can put any data type I want. For the keys, I can put any data type I want. So here, for example, B equals A for lists, B for tuples, C sets, D dictionaries. So the key is a string and the value is a string. So B of C here becomes sets. And I also want to stress that tuples have enclosed by parentheses, dictionaries enclosed by curly brackets, lists are enclosed by square brackets. Remember this stuff. Okay, conditional statement. If something is true, then do something. So if, let's say, S is equal to Ahmed. If S is of 0, which means that if the first letter of the string is A, so S of 0, or the first element or the first letter of the string equal A, print S. Let's see how this is running. Ahmed, yeah, so I'm printing Ahmed because this actually is true. So the if statement works like this. If some Boolean expression, execute the statement. If that is true, evaluates as true, then this statement is printed out. Elif, if you have other conditions, let's say temperature is 15. If temperature is less than 15, print this out. Elif is otherwise, or else if. For some reason, someone decided in Python that else if becomes elif, no idea why, whatever. Elif temperature is less than 20, print that. Else is if all the elifs run out. If all the conditions are false, then do this. So if this is false, and all the other elifs are false, then do this one. Okay. Loop, the loop statement, for loop. How it works: for k in some list. So if I wanna run a loop with some index, let's say that index is k, that index is gonna be a member of some list, and then the way the for loop works, it gives a value for k by going through the list every time. So it iterates k through 1, 2, and 3. So when I run this, it gives k 1, gives k then 2, and then gives k 3. So this is really how very basic for loop works. Loop means that it's a statement that's going to be repeated. Okay, it's not like the conditional statement for the if statement. If statement is a statement that executes based on a condition, logical condition. A loop statement executes based on, it repeats based on some condition. So as long as k is in this list, keep repeating the print k. The while loop is a bit more open or more generic than the situation with for loop. So in the while loop, while x perform these statements, so while x is true, keep running these statements. So a equals 10, while a is greater than 0, as long as a is greater than 0, keep printing a, and then subtract 1 from a. Minus equal means a equals a minus 1. It's another way of writing it. So we can do this here, and you see it goes from 10 down to 1, and then stops, because when a is 1, it becomes greater than 0, and then a becomes 0, 0 greater than 0 is false, so the while loop stops. Okay, now as we head towards the materials project stuff and the libraries related to the materials project, one key thing in Python is it's a modular language. You can use other people's code, and that's why when I say let's download or let's set up a library or let's use a library. If you have a library, there are a couple of libraries that you can install for Python. There are actually thousands of libraries you can install for Python, such as NumPy. You can install NumPy, and then to use NumPy in your code, you just go import. So the import statement is a statement that lets you use other people's code. NumPy is very popular mathematics library, one of the most popular ones. For example, if you want to do the log or a sine or a cosine or any of these complex mathematical functions, you just go import NumPy as NP. It gives us an alias, and then NP, that's the alias for NumPy.log. So that's just the logarithm of 11. That's the number. 2 point blah blah blah. Okay, now so far that was all Python. Now let's go into the materials project. The materials project is a great materials database. It's available online for free. You can sign up. If you want to access materials project via Python, you have to request for an API key. All this information is available on their website. And let me just show you here an example of a page from materials project. That's the page for carbon, the carbon material. Materials project has 124,000 inorganic crystals, by the way. And it has a lot of other types of crystals, but we are going to focus only on the inorganic crystals. So for example, you can go to materials project and search for diamond by choosing carbon, and then looking for the correct symmetry to obtain diamond. Actually, let me show you. I'll do this very quickly. But in order to use all these features in materials project, you actually have to sign up. So, and it's all for free. So carbon, search, gives you the periodic table like that. Then you can put whatever combination of elements you want, and then it's likely that you're going to find some material there. Now MP66, that's the diamond that I'm looking at. And this is the page for diamond or materials project. It allows you to play with the structure. It gives you some basic material information, like the band gap, for example. And by the way, every single thing here has been obtained via DFT. So people use density functional theory in order to obtain all of these. They're all calculated quantities. Okay, now going back to, so that's the page. I put a snapshot here. All of these are DFT properties. So for a given element composition, the lattice parameters and positions of the atoms have actually been obtained by DFT or optimized by DFT. All of these quantities that you see here are all obtained via DFT, density functional theory. And then further DFT calculations have been performed for a group of elements in materials project to obtain more quantities. Okay, so Tanweer, it's predicted by DFT, and some of them are close to experiment, some are not close to experiment. As you know, DFT is, has issues with band gap prediction and some other properties. No worries. Okay, now to be able to access and to obtain data from the PyMatGen library, from Materials Project, the Materials Project team developed PyMatGen, which is a library that you can install on your Python to be able to access Materials Project. Let me show you quickly how to install PyMatGen on Google Colab. Just type this, copy paste this stuff, type it, and then hit play, and it's gonna run all these. It's actually installing PyMatGen on the cloud, man. That's pretty cool. If you want to set up PyMatGen on your computer, just go pip3 install PyMatGen. Now, PyMatGen can be used for a range of things. For example, you might have heard of the CIF file format you get from XRD or from websites or materials. So all the materials on Materials Project are available as CIF in a CIF format, you see, and then you can download the CIF like that. I'm now downloading the CIF for Diamond, for example, but I already have it, I don't need to. And then these are the commands that let you open the CIF file in Python. Just do that. Oh, sorry. So parser equals CIF parser. This is a class in PyMatGen that can open the CIF file, and then that's if you're keeping it on your computer. But if you're running it from here, then you can, instead of this, you can use this line, and it's going to actually open the PyMatGen from a remote location. Let me see if since that I destroyed my blog. Yeah, it actually is running. That's cool. Okay, so I kept this CIF file on my blog page on the server, so you can actually open it from there, and then using this CIF file or CIF file object, it's a Python object, some computer science jargon around object-oriented programming. I know there's a very quick tutorial, so I'm gonna have to skip a lot of details. So now here I'm able to, I have all the CIF information in this parser object. Now I can use this parser object to get information about the structure. So for example, that CIF, it's an alloy zinc 9 Fe4. I can actually print out the CIF information as text here, so it gives me all the lattice parameters and positions of the atoms. And I can, request specific information from within that object. I'm just giving it here a nice name, ZN9F4. It's just a variable here, just to make it easy, easier to access it. And then equals structure 0. Now lattice is going to give you the lattice parameters. Here it is. If I want the species, here are the species. You see? If I want the charge, just in case you need the charge, 0, of course, it's an uncharged material. If I want the Cartesian coordinates for the elements, here they are. So the first element, Zn, is in this position. This Zn is in this position, and so on. So all of these Cartesian positions correspond to the species here. Atomic numbers, if you want atomic numbers, and distance metrics, if we're gonna play with the distance metrics next week, or I'm sorry, next tutorial. I'm not sure when it's gonna take place though. Okay, querying structures with PyMatGen. That unfortunately we only have 2 minutes. I think I'm gonna have to skip this part, but just very quickly, this code enables you just need to put in your API key here, and then you're able to query, for example, all the materials, get all the material IDs for all the materials that have a band gap greater than 1. Right now, there are 44,000 such materials. And then this code prints out the material IDs for the top 10 or the first 10. I can take this material ID, go to materials project, put this material ID here, and there you go. So that material I'm opening right now has a band gap that's greater than 1, and just in order, to make sure that I'm not fooling around, here it is. It's actually 1.032. It actually works. So that's the way to query materials project using Python. Yeah, that was a lot to squeeze in 40 minutes. We're 1 minute away from the last time Zoom gave me extra time, but today these guys are acting more thrifty. But anyway, I hope this has given you just a bird's eye view of how to use Python and the different features in Python that enable you to access materials and go to materials project and play with the data there just via Colab. We got extra time. Man, they didn't tell me anything. Okay. Yeah, 1 second. Participants. Okay, I'm gonna pretend we have extra time until something happens. Okay, so sorry, yeah, also saw the extra time. Okay, beautiful. Okay, I'm gonna assume, yeah, we're still on. Okay, it's 40 past, so. Okay, thanks, Irene. Lovely. That's great. So maybe I'm gonna just go a bit more slowly in this last bit that I covered here. I'm gonna go back to PyMatGen Python library because I went really, really fast here. So PyMatGen library is a Python library that you can set up very easily on your computer or on Google Colab, like I did here. And it enables you to manipulate crystal structures, to access or to query the materials that exist on materials project. Materials project, again, just for you guys to remember, it's a project that it hosts a huge number of materials. So what's on materials project, just give you an idea of what's right now there. So materials project has this, that's the number of materials that are there right now, almost 500,000 nanopores materials like MOFs and stuff. Inorganic compounds, a huge number, 124,000, that just keep increasing. 35,000 molecules, all of this stuff is on materials project. So what materials project does, it creates a structure and then optimizes it, uses DFT to optimize it, to optimize the atomic positions. And like say here, for example, all these atomic positions have been optimized with DFT. Even the lattice parameters have been optimized by DFT. Also, it tells you what it used, for all of these optimizations. So the input files that these guys have used to do that, and they do this all using the software VASP, very popular software in DFT. And it lets you, play with the structure like that. I'm going to remove the polyhedra, remove the bonds, and so on. And it shows you the band gap and a few, like the magnetic moment for like a ferromagnetic material. It's 8 μV here. For the band gap, all of these quantities have been calculated via DFT as well. Now, why this materials project database is so amazing for machine learning? Whenever there is a lot of data is always a good thing for machine learning. One of the things that people have been doing over and over with materials project, even including myself, I would get a lot of material. Oh yes, Fatima. So the paper that I referred to, not mechanical properties. What sort of properties? Like, can you give me an example of a mechanical property? Elasticity? Yes. People actually did that. So there is I think there is actually a paper on hardness. You look it up, just type DFT hardness machine learning, and you probably would find there. Images of the structures. You can actually download the CIF, and you can open it via a software called Vesta. So just download Vesta to visualize your CIF files. Okay. So you can, I mean, in my own paper that I referenced here in the notebook, it's up there, somewhere up there. In that paper, I predicted the specific heat capacity and the entropy of some of the materials on materials project, and all the code that I used is available on the blog, again, which I broke. So I'm definitely gonna work on it. Is it possible to do machine learning with molecular? Absolute. Oh, molecular dynamics. Well, molecular dynamics is one of those methods. MD, or I thought of initially, I thought of DFT MD. Well, MD, it depends. I mean, I've seen people doing MD simulations, and you know, I'm predicting MD calculated results uh, um, using machine learning. So as long as you have a specific quantity that MD gives you, and gives you after a number of runs. It's not just that you run one MD run, for example, and here, there you go. Here is the melting point, for example, or here is whatever property. It has to be a property that you obtain in a valid, you know, in a valid way. Otherwise, the outcome of your machine learning predictions will be questionable. And that's one of the, you know, one of the things about DFT is that it's a ground state theory. And I mean, there are no, if you're using the same software, you're gonna get the same results for a given number of atoms or for a given material every time you use that software. So like, whereas in MD, you start from a configuration, it gives you a result, maybe a different configuration gives you a different result, even using the same force field, the same software, the same crystal structure, the same number of atoms. So that's, I mean, that's why a lot of people using machine learning have been doing it with for quantum chemistry or for inorganic crystals. I haven't seen a lot for MD. Eventually DFT, you know, compared to. Okay, I'm not doing DFT using machine learning. I'm actually doing machine learning to replace DFT. Yeah, that's that's the news. So why I'm using machine learning is because DFT is expensive. It's you know, for example, right here on the screen, you see the band gap. To calculate the band gap, it takes a lot of time, a lot of computational time to actually do that. We use a supercomputer to be able to do that, especially if the number of atoms within the crystal are actually large, and you're looking for accuracy. I mean, you can get a crappy band gap with crappy accuracy, but if you want high accuracy, you're going to use a high accuracy software with high accuracy parameters to get a number like that. So uh, this is very expensive in terms of time and in terms of resources, and therefore people are looking for various ways to predict various parameters that are normally calculated using DFT, using machine learning instead of DFT. Piezoelectric, absolutely. Yes, actually, that's a project actually I was working on, and I've seen people doing stuff like that because there are some piezoelectric properties that have been predicted using DFT. Okay, so going back, by the way, please go ahead and ask. I'm opening the Zoom group chat. The point really here is to interact if you have questions. I'll just keep going, and if you have questions, just throw it. So that's the carbon page, the diamond page on materials project. Now the DFT properties that we find there, that's what I already said. Why materials project is great for machine learning. I've seen it myself. A lot of people have been doing it. It has a lot of data, it has a lot of materials, and a lot of calculated properties. So you can create the data set from materials project, and also you can create the targets or the target properties from materials project. Remember, in machine learning, there is, you know, there is the data set, and the data set is like the set of, you know, materials and their calculated descriptors. That's one side. That is the input of your machine learning. Remember, that's the input. The output of your machine learning is going to be the target properties, the quantity that you want to predict. Okay. Now, PyMatGen enables you to do the dataset part. So we can download materials, we can manipulate materials, extract properties from materials, and what we are going to be doing in the next tutorial, calculate descriptors, very basic descriptors, to be able to predict other, target quantities, which will be the band gap in our case. So you can just go and type this in your Colab, and this is what you're going to get in your Colab: downloading, collecting, downloading. This is basically setting it up. Or you can go on your console if you're using Mac, or if you're using Windows and you have Python already installed, you can just go pip3 install PyMatGen, and it will install PyMatGen for you. The link to my tutorial is right here. For everybody who arrived a bit late, here's the link. No worries. Okay, so let me just go a bit more slowly into this code. So you guys remember, no worries. You guys remember when I said that PyMatGen is a library that we're gonna import? So we need to import PyMatGen to be able to use it. We can import a specific class for PyMatGen to do a specific task. Here the task is to open a CIF file. So I can do this by importing, the CIF parser. That's the class that is going to be doing what I need, and then request equals. So I mean, I haven't gone into details of what this means, but for now, just think of it as a requester function that requests to download that file, converts it to text, and then passes it into this variable. So CIF file is actually a big string. So I'm converting this file here into a string, and then passing the string, boom, here into the CIF parser or class. When I call this line here, the CIF parser class takes the CIF file string and then creates for me a CIF parser object, which I call parser here. Next thing is we want to play, and we want to see what's going on inside this structure. So from the parser, there's a function called getStructures. So I call it, and then it returns a list of structure objects. I just need the first one, which is really the only one that I have. If you want to know what are the properties of that Python object that is going to be returned, I gave you the link here. Next thing is I'm printing that object. So here is the structure object being printed. It has the formula for the structure Zn18F8, or the reduced Zn9Fe4. That's the ABC and the angles, the lattice parameters, 6 lattice parameters. Number of sites is 26, and then there you go. So that's the unit cell for that crystal. But when we start working on the next tutorial, when we start actually working on creating descriptors, we want to start extracting information, numerical information from that object, from that stuff. To do this, PyMatGen gives you a few. You see this dot something. So dot something means the object or the structure object. Dot, I'm just calling the lattice data. So I just need the lattice data from that object. This is going to give me the lattice data from the object. So by the way, if I want to comment a line or remove a line from execution, I just put a hash. It will be neglected. So I do this. You see, these are the lattice vectors. These are the lattice vectors. Species dot species means I want to find the species in my system, and there you go. That was 26 species, right? 26 species. Each of these species exists in a specific Cartesian position. How to get those? I go cart coordinates. So cart coords, these give me the Cartesian position for each of those. So this first Zn atom exists in this, and all the units of all of these is angstroms, by the way. Okay. You can also get, instead of the element labels, you can get atomic numbers. 30, that's for zinc. 26, that's for, 30 is for zinc, and 26 is for iron. Now, the next thing is, so this is how we manipulate CIF files, which we will be doing a lot of this in the next tutorial. Now, what we also are going to do is to query structures using PyMatGen. Let's say you want to create a data set that's all the semiconducting materials on the database that have a band gap larger than 1. There's actually a syntax to do this that you can learn from Materials Project website. Just go there, read the documentation, read the help. All of this is explained. They actually have a video, man, a series of videos. I love this. Yeah, video tutorials. Look at this. So a lot of this is actually, a lot of these are very, very useful. They explain how the details of this stuff work. So this is a query statement. So results M here is the PyMatGen object, or the MP rester object. MP rester is an object that lets you interrogate or like query the database. What you put here is the API key that they will give you. So when you sign up for free, they will give you an API key. You have to put it here. Now, why do I put X's in my API key? Because these guys said on the website, I cannot share my API key with anyone. Well, there is actually a rationale. Every user on PyMatGen with every registered user has a number, like a fixed number of daily, I think, or maybe monthly queries, because these guys are doing it for free. But this doesn't mean that I can query as many as I can, or as many as I want. There's actually a limit to how many you can query for free. Not sure if there's a paid scenario though, but anyway, so you have to use your own API key here. It's just go there and see how it works. So results equal. Now query is the popular Materials project, or the PyMatGen function. It takes here the query parameters in a specific language, like for people who know JSON, this pretty much looks like JSON. Now GT, that's greater than. Obviously, if we go LT, less than, right? And there are a few others, all documented on the website. Properties, these are the properties that I need. I can actually get the material IDs. I can also get anything I want from these materials. So the properties can be material ID. I can put comma here, and then I can get any other thing, like a CIF file, for example. I can get a CIF file. So the result object, when this finishes, is going to contain all the material IDs and all the CIF files, okay, that are what do you call, satisfy this query condition. Let me just remove that for now. So when I run this, it's going to be it's going to run through all of the 44,000. It found 44,000 materials with that band gap condition, and then it runs a progress bar, and then results now has all the material IDs with this band gap. And so all the 44,325 have a band gap larger than 1. And here I'm printing out using the colon in an array in Python. I didn't really cover that. I told you it's very quick. So just quickly, this is giving me a slice of the array. So from 0 to 10 means I want all the elements from element 0 up to element before 10, actually. It's from 0 to element 9. But I have to put 10 here. If you want to know more, you can just access Python tutorials. Let me just give you a hint, a few nice Python tutorials I found. So let's say Python tutorial. So I usually would go like this one, for example, learn Python full course, 30 million. I mean, of course, you just go to this one. This guy is awesome, by the way. His tutorials are really good. So just put the links. Put the link.
Of course, I'm going to teach you everything you need to know to get started programming.
Thanks, mate. Yeah, that's it. So that's all for today. Anyone has any questions? Thankfully, we have some more time. Any questions? You can either type your question or you can just use the mic if you want. Okay, any questions? I will share the video recording on my blog and send you the link in an email. Okay, maybe that's it for today. I'll, as I just wrote here, I'm going to share the video on my blog, and I'm gonna no worries, no worries, and I'm gonna post it there in a blog, and we'll send you this information all in an email via Eventbrite, and we'll also announce the next session very soon. So thank you very much for your attention and for attending, and enjoy the rest of your day. Goodbye.